Hi guys, welcome to today's lesson on trigonometry. Today's meant to be an introduction. If you've had honors geo, you've had some trigonometry related to right triangles. So this is a review for you. In Algebra 1, I know Mr. Ratante goes over it, but it's pretty quick at the end of the year. So if you're not doubled up, this lesson is meant for you to make sure you lock in all 6 trig functions today. We're going to use these trig functions to derive our unit circle next block. So let's get started. I have a quick do now for you. I want you to pause the video and answer these questions. Are these two triangles ABC and A prime B prime C prime similar? Are they one of our special right triangles, 30, 60, 90 or 45, 45, 90? Label the angle measures in each and find the 6 following ratios of their side lengths. So here BC is 1, AB is 2, so that ratio would be 1 to 2 or 1/2. So pause the video and answer these questions. All right, so that number 1 and 2 were meant to be a review of the last 2 classes on special right triangles. Here we notice the shortest side of this triangle is 1 because radical 3 or square root of 3 is about 1.7. So our short leg here is 1. What do we do short leg to long leg? We multiply by radical 3, and that's what we get, 1 radical 3. And what do you do to the short side to get the hypotenuse is 2. You multiply by 2. So here we have a 30, 60, 90 triangle and the same thing in the bottom. We multiply by radical 3 and multiply by 2. So this is another 30, 60, 90 triangles. The next thing I asked you is find the following ratio of their sides. So I did the first one for you. BC to AB was the ratio 1/2. And if we go into its similar triangle, B prime C prime to A prime B prime, is also 2/4, which reduces to 1/2. Then I asked you AC to AB. You should have gotten radical 3 divided by 2. And then A prime C prime to B prime C prime, A prime B prime is 2 radical 3 to 4, which also reduces to radical 3 over 2. Do you see a pattern forming? And the last one, BC to AC, here is 1 to radical 3, and B prime C prime to A prime C prime also reduces to 1 over radical 3. So, something very interesting here. These similar triangles had the exact same ratio of sides, and what trig functions are functions that are assigned for an angle. So here I'm using angle A, our 30-degree angle. And what you notice in the first two is that BC and AB, from angle A, that's the opposite side divided by the hypotenuse. Here, B prime C prime to A prime B prime is the opposite side to the hypotenuse. We assign that the trig function sine. So for all similar triangles, there are infinite similar triangles. These are both 30-degree similar triangles. If I put a 30 in there, the ratio of the side lengths would be the same. Now, the next two, we're talking about AC and A prime C prime to the hypotenuse. So here, if I use this angle A, I have the adjacent side to it and the hypotenuse. Same ratio as this adjacent side to that hypotenuse. We assign that cosine, or cos of an angle. Now, if you look at your calculator above the 789 button, 2 above it, you'll see sin, cos, tan. Those are the trig functions that we're deriving right now. And then the last one you see on the calculator is tan. Tangent of an angle is always going to be the opposite side divided by the adjacent side. All right, so we have a little acronym to remember that sine is always the opposite side from that 30-degree angle divided by the hypotenuse. Cosine is always going to be the adjacent side divided by the hypotenuse. And tangent is always going to be the opposite side divided by the adjacent side. All right, so we're going to find these 6 trig ratios. And for the first one, we're relating or focusing on angle P. So I want the sine ratio of angle P, sine, so opposite over hypotenuse. So I go to P, angle P is here, and I need the opposite side from angle P. So opposite 15 over hypotenuse 17. Done. Now, it's not the same sine ratio for angle Q. If I want the sine of angle Q, it's still so, opposite over hypotenuse, but I want the opposite from angle Q. So the opposite from angle Q, the side is 8, divided by the hypotenuse is always 17. So notice, depending on the angle will depend on what ratio you're finding. Now, cosine, ka, I need the adjacent over the hypotenuse. So when I go to angle P, here's my angle P, my adjacent side right next to it is 8, divided by my hypotenuse, 17. But from Q, my adjacent side there is 15, divided by my hypotenuse, 17. So I get 15 over 17. And the last one, tangent of angle P, well, tangent TOA is opposite 15 over the adjacent side 8. So I have 15 over 8. And the tangent of Q, TOA, I need the opposite 8 divided by the adjacent side to Q, which is 15, and I get 8/15. So that's how easy it is to find the ratios of sides for each trig function as long as you know so, ka, toa. All right, now let's find our reciprocal function. So what about cosecant, secant, and cotangent? Well, just as easy. Cosecant, you know, is the reciprocal of sine, and we already found sine of P to be 15 over 17. So what do you do to get cosecant is you do the reciprocal. You flip it, and you'll get 17 over 15. For cosine, ka, we already found adjacent over hypotenuse. How do you get secant? Secant's the reciprocal of cosine, so you flip it, and you get 17 over 8. So do you see where you don't really need to remember 6 different ratios? If you know SOHCAHTOA, toa, you just flip it to get its reciprocal. And then tangent of P, toa, we already found to be 15 over 8. So cotangent is the reciprocal of tan. You flip it, and you get 8 over 15. So there you found your first 3 reciprocal functions, cosecant, secant, and cotangent. All right, now that's what we're going to use for finding side lengths in triangles is your SOHCAHTOA acronym. So here you're going to be missing side lengths in all 3 of these examples, and we're going to be able to find those. Now let's look at this first one. You can't use Pythagorean theorem, so that's out. It's not a special right triangle, so that's out. But we do have trigonometry. You can find missing side lengths if you can lock in one angle. So the first angle I'm going to use here to show you there are many different ways to solve this. We're going to use the 51-degree angle. I'm going to lock it in. The side I need, x, is opposite 51 degrees. And the only side that I do have is adjacent to 51 degrees. So I'm going to use tangent, toa, opposite over adjacent. We do not have the hypotenuse, so tan is the only trig function we can use. So I set up my trig ratio that the tan of 51 is equal to that opposite side x divided by the adjacent side 10, and I'm going to solve for x. Now what you can do is put tan 51 over 1, or you can multiply both sides by 10, and you'll get x is equal to tan 51 times 10. So take 10 tan 51 straight in your calculator, make sure it's in degree mode, and you get 12.3. Now, what if you wanted to lock in the 39 degrees to show you how many different ways there are? Let's lock in 39. If I want to use 39 degrees, well, that 10 is no longer adjacent to 39. It's actually opposite the angle 39 that I've locked in. And the x is not opposite, it's adjacent to 39. So to show you those trig ratios lock in and are dependent on the angle you choose. So here's the second way we could have done this problem. I could have set tan 39 equal to opposite 10 divided by x, what I'm looking for. Now, here you can multiply both sides by x, divide by tan, and you'll solve x is tan 10 divided by tan of 39 degrees straight on your calculator, and you get the same answer. to show you there are multiple ways to solve these. It's whatever you see. All right, the second one, I have one angle locked in at 24, so I'll use it. You could subtract 90 and 24 from 180 and use this one, but I see right away that I have the opposite side is 4, and I need the hypotenuse, the longest side of this triangle. So opposite hypotenuse, OH, I need to use sine. So sine of 24 is the opposite over hypotenuse. I set up the ratio of those sides, and I'll solve for x. Again, you can switch them, or you can multiply by x, divide by sine 24 to get x alone. And straight on a calculator, 4 divided by sine, it's going to open up, put in 24, and you should have gotten 9.8. All right, and the third one here, I have a locked-in angle at 40 degrees, and again, I'm looking for the hypotenuse, but I don't have the opposite side. I have the adjacent side to the 40 degrees. So adjacent and hypotenuse, AH, ka, is cosine. So cosine of 40 degrees equals that adjacent side 6 over the hypotenuse x. And again, I can cross multiply, or you can flip these, and you get x is equal to 6 divided by cosine of 40, or 7.8. So there are 3 good examples for your notes on how do you use trig functions to find sides of right triangles. When Pythagorean theorem doesn't work, specials don't work. All right, so let's move on and talk about their inverses. So take a look on your graphing calculator or any calculator. Right above sine, cosine, tangent in light blue, you will see the 3 inverse functions: sine to the -1, cosine to the -1, tan to the -1. So we use inverse functions of our 3 basic trigs to find angle measures. So we're going to use inverses of those 3 trig ratios to find angle measures. So again, I'm using that same problem that we started with, and I want to find angle Q. Now, I already knew how to find my ratios, so I'm going to lock in angle Q and show you there are 3 ways. You can use any of these 3 to get your angle Q. So I know it's going to be the inverse of a trig ratio. So I'm going to first use sine, because I know 8 over 17 was equal to my sine. So if I take the inverse of that ratio, I will get 28.1 degrees. So all you need to do is hit second sine. It'll come up and wait for that ratio to be put in. Plug it in, hit enter, and you'll get 28.1 degrees. Now, what if I wanted to use the 15 here instead? Then you would use cosine, because I have the adjacent side to Q, 15 divided by 17. I can use the inverse cosine of 15 over 17 and get the same answer. Or if you like tangent, I don't have to use the hypotenuse at all. I'll use the opposite and adjacent side and use tan. The inverse tan of 8 over 15 will give me that degree measure, 28.1. So you see there are many different ways to do these trig problems. Now, what would the 3 trig ratios be for angle P? So you'd lock in on angle P, or you already know this is 90, angle Q is 28.1, so you don't even need to use trig. Subtract them from 180 and you get 61.9. So I may be asking you in the Do Now Exit ticket today to find angle P based on the 3 trig functions. All right, so that is finding or using inverses to get angle measures in triangles. So let's try 3 together. All right, so first one, we're going to round to the nearest tenth. I'm looking for angle X degrees here. I have the opposite side from angle X, and I have the adjacent side. SOHCAHTOA. Is tangent, so I'm going to set up my trig function. I have the opposite, the adjacent, so I'll use tan. Now, this is the trig function you would set up. How do you get rid of tan? Well, you take the inverse tan of both sides, and x is the inverse tan of that ratio. Straight on a calculator, you get 47.7 degrees. Pause the video at any time and try these, and make sure you can get to those answers. All right, the second one, I have an x again, angle measure I'm missing. I want to find it. From that x, I know I have the hypotenuse of the triangle and the opposite side. So OH, so I'll use sine. So x is the inverse sign of that ratio, opposite over hypotenuse. Plug it in and you get 57.5 degrees. Third one, here I'm looking for angle x. I do not know the opposite side. I have the hypotenuse and I have the adjacent side right next to angle x, 3 over 3 radical 5. So I can find that angle measure by taking the inverse cosine of adjacent over hypotenuse straight on a calculator. You don't need to rationalize, and you get 63.4 degrees. So when you're trying to find angle measures in right triangles and you have two sides, you use trig to find those angle measures. All right, so to wrap it up, how many ways do we know how to find side lengths in right triangles? Well, we have our good old Pythagorean theorem if we know two sides. We have our two special right triangle rules, 30, 60, 90, 45, 45, 90. And you now have trigonometry, SOHCAHTOA, to help us find it if we don't have two sides. What if you only have an angle and one side? You can use trig to find those other sides. All right, so your exit ticket today when you take attendance is going to be to find side D and E using two different methods. Can we use Pythagorean theorem? No, we only have one side. Special right triangle, yes it is. So this one's pretty easy. My short side across from 30 is 2. So my long leg is going to be 2 times square root of 3. My hypotenuse is going to be double that, or 4. The trig way would be to lock in an angle. Here I'll use 30 degrees. To find D, the long leg of this triangle, you could take, you could take the two opposite side and divide by the adjacent side. So you have TOA, OA, opposite over adjacent. You could set up tan of 30 degrees equals 2 divided by D and solve for D. To find E, you have the opposite side and you're looking for the hypotenuse. So you could set up OH, so sine of 30 degrees equals the ratio 2 over E and solve for E. You could use 60 degrees and set up those ratios as well with tangent and with cosine. So the choice is yours. You're going to be asked in the exit ticket, hint, hint. So that's how I'll know whoever gets this correct was watching this video. I gave you the two different methods to solve for side D and E in this right triangle. Remember, these three methods only work for right triangles. So if you don't see a right angle, the angles don't measure up to get you a 90-degree angle, you cannot use these. All right, have a great day. You're going to work on the classwork today and finish the exit ticket. Next block we'll be practicing. Have a great day.